but well, let me actually tell you then about rather than the proof. I think I'll share the proof with Gil, because the proof that I wanted to actually show you gives a proof of stochastic gradient is well behaved on both convex and non-convex problems, and the proof I wanted to show was for the non-convex case because it applies to neural networks. So you may be curious about that proof, and remarkably that proof is much simpler than the case of convex problems. So let me just mention some very important points about stochastic gradient. So even though this method has been around since 1951, every deep learning toolkit has it, and we are studying it in class, there are still gaps between what we can say theoretically and what happens in practice. And I'll show you those gaps already and encourage you to think about those if you wish. So let's look back at our problem. I'll tell you about two variants. So here are the two variants. I'm going to ask if any of you is familiar with these variants in some way or the other. So I just called it feasible. Here there are no constraints, so start with any random vector of your choice. In deep network training, you have to work harder. And then this is the iteration you run, right? Option 1 and option 2. So option 1 says, that was the idea we had in class, randomly pick some training data point, use its stochastic gradient. Well, what do we mean by randomly pick? The moment you use the word random, you have to define what's the randomness. So one randomness is uniform probability over n training data points. That is one randomness. The other version is you pick a training data point without replacement. So with replacement means just uniformly